We're going to summarize in this video some applications of Newton's laws. And we've talked about a bunch of different applications so far, but like I said, this is going to be a little bit of a summary. So first off, our stand on the desk, shout it out from the rooftops equation would be F force equals m mass times a acceleration. And this is always true. So if you're talking about any other kind of forces, you can set them equal to mass of the object times the acceleration of the object and solve for either one, or if you're solving for anything having to do with forces, force always equals mass times acceleration. So given any kind of equation, you can always set it equal to ma. Another important piece of Newton's laws is that we can sum up forces in different vector directions. So we can have the sum of the forces in the x direction. So remember that symbol sigma means sum, or if you add up all of the forces in the x direction, that would equal ma. Also the sum of the forces in the y direction, every single force in the y direction. A lot of times when we're talking about the sum of the forces in the y direction, one of these will be weight and one of them might be the normal force. Oop, this should be a 2 and a 3. And if something is in equilibrium, so equilibrium, the sum of the forces in any direction, so whatever is here in this, that's supposed to be dashed lines, but my stylus is not quite small enough. If anything's in equilibrium, the sum of the forces in either the x or the y or the z will always be 0. So that means that we have to have some forces going one direction, so maybe positive x direction, while some are going in the negative x direction, and they will cancel each other out and equal 0. So a lot of times if we have something hanging that's not moving, we would have its weight going down and a tensional force going up, and they would be equal to 0. And when we're measuring force, we measure it in newtons, in the metric system, or force is measured in pounds, or pounds, in the empirical, or the USA version. When we're measuring mass in the metric, it's measured in kilograms, because a newton, 1 newton, is a kilogram meter per second squared. Whereas mass in the empirical is slugs, and 1 pound is equal to a slug, feet per second squared. And remember, when we're measuring weight, we have the force due to gravity, and that is equal to mass times gravity. So we might feel a sense of weightlessness when we are free falling, because the acceleration of free fall is gravity going downwards, and therefore if we have our force due to gravity is mass times gravity, we would have, and that's going down, we have no force going back up. So our apparent weight, I'm going to write that like this. Our apparent weight would be our force of gravity plus whatever force is going back up. So a lot of times that's mass times acceleration. If our elevator is moving, or say we're standing in an elevator, if our elevator is moving either up or down, or if something is lifting or lowering us, we feel an apparent weight as seen by the elevator lab. So we have our force of gravity going down and our mass times acceleration going up or down. But when our acceleration is equal to gravity, then we have these terms cancel out and they would be equal to 0. Sorry, everything went blank there, but just ignore that. So now let's talk about the normal forces. So if we have any surface, no matter what it looks like, the normal force is always perpendicular to the surface. And we calculate the normal force of acting on an object by talking about the angle at which the normal force is compared to the force due to gravity directed straight down, and the magnitude of the force due to gravity. So when we have a normal force, we have to say that it acts, it uses its vertical component as F sub g, and this angle here, theta, is the same angle at which the plane is inclined. So, using SOHCAHTOA, we can say that adjacent over hypotenuse, therefore cosine, would be what we need to find our normal force, because our adjacent, so cosine theta, is equal to F sub g over Fn. Therefore, Fn is Fg over cosine theta, if you rearrange using algebra. And we have multiple kinds of friction. We have static, that's when it's not moving, and that is equal to mu Fn, that's the coefficient of static friction, and that's the normal force. We have kinetic, and that's when it's moving, and that is also equal to mu Fn, but this is the coefficient of kinetic friction. So objects have different kinds of coefficients depending on if they're moving or not, and you can solve for the kinetic friction force by talking about applied forces. And it's always in the opposite direction to which an object slides across a surface. And it doesn't depend on the object's velocity.